Okay, by now you must have understood the physical significance of the de Broglie wave and the matter wave. And one thing we can notice from that there is uncertainty in locating the particle or the matter position within the wave group. Within the wave group, if you see, this is the wave group. Within the wave group, which is a matter wave, so there is uncertainty in locating the position of the particle within the wave group or the matter wave. Whether the particle is here, is likely to be here, likely to be here, likely to be here. There is an uncertainty in the matter wave of finding the particle. So now we are going to take up the quantum mechanical uncertainty principle, which says that we cannot know the future because we cannot know the present. And in the simpler version, it says that it is impossible to know both the exact position and exact momentum of an object at the same time. So the exact position and exact momentum, we cannot measure the exact position or the exact momentum, not or and. We cannot measure both at the same time, and this is just because of the uncertainty. So before going to the details of the uncertainty principle, first let us understand that if I have a sine wave like this, so in this sine wave we have a precise wavelength of this sine wave. Okay, we have a precise wavelength because the wavelength is fixed in this case. So because the wavelength is precise, so we can precisely determine its momentum. Okay, because we know that P is h by lambda. So if we know the wavelength of this wave exactly, precisely, so we can say that the momentum of this sine wave is the exact. So a sine wave of wavelength lambda implies that the momentum is precisely known. But the wave function and the probability of finding the particle, okay, psi star psi, this is psi star psi, is spread over all space. So the momentum is known, momentum is exact, but what about the position? It is spread across all the wave. The position of the particle whose momentum is exactly this, and the wave associated with the particle is this. The particle could be any time here, or any time here, or any time here. So we cannot say precisely at the same time the particle is having momentum P is either at this position or this position or this position. Fine. So in order to precisely measure the location, if you want to precisely measure the location of this particle whose sine wave is this, what we need is a group wave. A group wave. And we know that how the group wave is there when we add several waves of the different wavelength together, will produce an interference pattern which begins to localize the wave. So if I have a wave of different, like this is another waves or lambda 1, this is of lambda 2, this is of lambda 3, this is another wave of lambda 4, this is another wave of lambda 5. So all these waves have different wavelengths, and if I combine all these wavelengths, they got interfere each other, then we have a wave group. So the position of the particle, which is varying because of this wavelength, is now contained within this wave group. Okay, so now what information we are going to get from this wave group? Okay, so you can read this, that when the several waves interfere to give us a wave group. So an isolated wave group is the result of superimposing of an infinite number of waves. So wave group is the superposition of infinite number of waves with different wavelengths. The narrower the wave group, the greater the range of the wavelength involved. So more the number of the different wavelengths, this wave group is going to be narrower. It could be like this. Okay, a narrow de Broglie wave group. This is a de Broglie wave group. This is another de Broglie wave group. Thus means a well-defined position. Delta x is smaller. So now if this is the wave group and this is another wave group, so the particle position is exactly in this wave group, and here there is a certain uncertainty. Could be here, could be here, could be here. Anyway, depending upon the narrowness of the wave group of the de Broglie wavelength, we can precisely have the well-defined position, because the delta x is a smaller. Delta x is smaller, but a poorly defined wavelength, because we don't have crest or trough in crew language to define the what could be the wavelength of this wave group. And since wavelength is related with momentum, so if you're not able to define the wavelength correctly, there is an uncertainty, then there will be uncertainty in the momentum. Okay, but a poorly defined wavelength has a large uncertainty delta p in the momentum of the particle the group represents. Okay, so a wide wave group means a more precise momentum but a less precise position. So now we know that if the wave group is wider, so if the wave group is wider, if you compare this wave group, this is more wider wave group, so we can very easily define the wavelength, but the delta x will be large. If we narrow our wave group, we cannot define the wavelength, and we can define the delta x. So the narrowness and the broadness of the wave group gives the uncertainty in momentum and the position respectively. So let us come to the statement again, that we cannot know the future because we cannot know the present, or it is impossible to know both the exact position and exact momentum of an object at the same time. So you can see that if the wave group is very narrow, so we cannot define lambda. What could be the lambda of this wave group? But the delta x is a small. So delta is small, but the delta p will be large. So delta x is uncertainty in the position, and delta p is the uncertainty in the momentum. So the uncertainty in the position will be small, but delta p will be large. Uncertainty in the momentum will be large because we are not able to define the wavelength. So there is an uncertainty in wavelength. So lambda and momentum are related. Okay, you know lambda is h by p, delta h. Okay, so if the wave group is broader, so we can safely define the wavelength, but the delta x will be large. So the uncertainty in the position will be large, but the uncertainty in momentum will be small, because we can know exactly what is lambda. When we know lambda, then we can precisely say what is the momentum. So it means that in the meantime, at the same time, we cannot know exact position or exact momentum on an object at the same time. So if and it is narrow, we can have only position exactly, define the position exactly, but we cannot define the momentum. If it's broader, we can define the momentum, but we cannot define the position of the particle exactly, of the matter wave. And you know that the particle that correspond to this wave group may be located anywhere in the group at the given time. And of course, the probability density psi square is giving you the maximum probability of finding the particle. Okay, so this is referring to figure 3.3, which is you can see is figure 3.3 is there. So if this is my psi, and if we find the psi square of this, so this will give us the probability of finding the particle is maximum. Where is the maximum probability of finding particle? So this position is giving us the maximum probability of finding the particle here, because the amplitude is maximum here. Okay, psi square will be maximum here. So this is what the uncertainty principle tells us about the matching the position as well as the momentum of an object at the same time. Okay, so moving forward, the expression for this uncertainty principle, the quantum mechanical expression for the uncertainty principle is delta x, and delta p is h upon 4 pi, or so we can write delta x delta p is like h cross, or h by 2 pi. So this equation gives you what? This equation gives you that the product of the uncertainty delta x in the position, uncertainty in the position is delta x, and uncertainty in the momentum delta p in the x direction. Because I am using x, that means the particle is moving in the x direction, at the same time is equal to or greater than h upon 4 pi. So the product of the uncertainty in the momentum of the particle which is moving in the x direction and its momentum in the x direction cannot be greater than, has to be greater than equal to h upon 4 pi. So I can write also like delta y delta py greater than h square, delta z delta pz greater than h square. Okay, fine. So this is what uncertainty principle tells about. And if you arrange matter so that delta x is small, corresponding to a narrow wave group, then delta will be large correspondingly. So if you reduce delta p in some way, a broader wave group is inevitable, and a large delta x will be large. Delta x will be large. Fine. So this is the explanation of uncertainty principle on the basis of the wave nature. So now, till now we are dealing with the wave. So this is the explanation of the uncertainty principle on the basis of the wave nature of the matter or the electromagnetic radiation. Okay, so h cross we can write h upon 2 pi. So we use the value of h, and 2 pi we can have 1.04. This is joule second, which you can understand. So uncertainty principle can also be written as delta x delta p is greater than or equal to h upon 2 pi. Fine. Now let us discuss the uncertainty principle on the basis of the particle nature. So can we say something about the uncertainty principle on the basis of the particle approach? What result does it gives? So on the basis of the particle approach, we can also explain the uncertainty principle, and that goes to measuring how to measure the position of an electron and its momentum when it is revolving in the nucleus. So what we do is actually we use the light of wavelength lambda. So if this lambda is its wavelength, its momentum is h upon lambda. When one of these photons bounces on the electron, okay, and then it will return back to our detector. So what happened is that the electron basically strike this and imparts its energy, okay, and then the electron gets its final momentum and the photon reflected back. So in this whole process, what happens? The photon, when it strikes the electron, it transfers its energy, momentum to this electron, okay, and then goes back. So what happens that the original momentum gets changed. So the exact amount of change delta P cannot be predicted, but it will be of the same order of the magnitude as the photon momentum. So the original momentum of the electron gets changed. So whatever the electron momentum was there when it was revolving inside the atom, when the photon strikes the electron, it imparts certain momentum, energy, and then with that the momentum of the electron changes at the same moment, and that change will be how much? The maximum could be if the photon of the momentum h by lambda transferred to the electron. So that change could be approximately h upon lambda. So from this concept, the longer the wavelength of the observing photon, the smaller will be the uncertainty in the electron's momentum. Okay, so if I measuring the electron with a wavelength which is greater, then delta will be smaller. So that means we can precisely measure the momentum of the electron. But if we think further, so because the light is a wave phenomena as well as the particle phenomena, we cannot expect to determine the electron's location with perfect accuracy, regardless of the instrument used. What does it mean? So a reasonable estimate of the minimum uncertainty in the measurement might be one photon wavelength. That is, delta x has to be greater than or equal to lambda. So what does it mean? So when the momentum changes, the wavelength changes. When the electron is revolving in the atom, it's at certain momentum, it's a wave property, and it's certain momentum and it's certain wavelength. So when there is uncertainty in the momentum, there's a change in the wavelength. Not exactly the change in the wavelength, there will be change in the position. Because when the wavelength or the photon strikes the electron, at the same moment it changes its location. When it pushes, at that moment, the uncertainty in the position, the limit on the uncertainty in the position will be approximately greater than or equal to the wavelength, because wavelength of the incident photon. Okay, so the shorter the wavelength, the smaller the uncertainty in the location. So you can see that if the wavelength is shorter, I can precisely measure the wavelength position, but if the wavelength is shorter, I have a more uncertainty in the momentum. In the same way, if longer the wavelength, we can precisely measure the momentum, but there will be more uncertainty in the position. So altogether, when a photon of certain wavelength strikes the electron, in order to measure its position or momentum, So depending upon the wavelength of the incident photon, either I can have the uncertainty more in the momentum or uncertainty more in the position. So the delta x delta p will be greater than equal to h upon 2 pi or h upon 4 pi. So on the basis of the particle nature also, the uncertainty principle is holding good, because the moment we measure the position and the momentum, try to measure the position and momentum of the electron by using a photon of certain wavelength, depending upon the wavelength of the photon, there will be a corresponding uncertainty in the position as well as in the momentum. Now let us do some application part of the uncertainty principle. For this, go to example 3.7, and it is asking about to show the lower limit on the energy an electron must have if it is to be the part of the nucleus. So let us first solve this example, and then we conclude out of this. So a typical atomic nucleus is about 5 into 10 to the minus 15 meter in radius. So means this is about 5 Fermi, because 1 Fermi is 10 to the minus 15 meter. So this is the radius of the atomic nucleus, and using the uncertainty principle, so we have to find the limit, the lower limit on the energy of an electron, which is inside, if this electron is inside this nucleus, because we know that inside the nucleus we don't have an electron. The electron is revolving outside the nucleus. So we have a nucleus, and then we have electron revolving outside the nucleus. But what the question is asking, that if the nucleus is of this size, this is of this size, then what will be the lower limit on the energy of an electron must have if it is to be part of the nucleus. अगर electron एक part of the nucleus है, it's not in this here, if this electron is in the nucleus, then what should be the energy of this electron? Let us do it. So using the uncertainty relation, you can see that, so because the radius of the nucleus is 10 to the power 15, it's like it's 10 to the power minus 15 meter, it's written minus 5. So the electron, if this is 10 to the power minus 15 meter, this is 5 into 10 to the power minus 15 meter. So the electron, if the electron is inside this nucleus, so then the uncertainty in position will be delta x will be this amount. Okay, and so once we know the uncertainty in the position, we can find the uncertainty in momentum using the uncertainty principle, that delta x delta p is greater than h square by 2. So putting the value of h cross, which is h upon 2 pi, 1.054. You have already seen that h cross is h upon 2 pi. This is 1 point this thing. So we can use the value and 2 in the uncertainty in the delta. So this comes out to be 1.1 10 to the power minus 20 kilogram meter per second. Okay, fine. So the uncertainty in position is about the radius, and this the uncertainty, corresponding uncertainty in momentum is this thing. So if this is the uncertainty in the nuclear electron momentum, so electron की position में uncertainty is how much? Is 5 into 10 to the minus 15 meter, and the uncertainty in electrons momentum is this thing if it is inside the nucleus. So now let's calculate the corresponding kinetic energy, which is due to this the momentum of the electron. So you already know this is the mass of the electron, This is m naught c square, which is rest mass energy, is 9.1 into 10 to the power minus 31 kilogram, and this is 10 to the power minus 20 kilogram. So we can treat the rest mass energy is, this is the momentum. So rest mass energy, if Pc is less than E naught, then this is classical, and if Pc is greater than E naught basically is m naught c square. So this is relativistic. Okay, fine. So now here Pc, the momentum is greater than the E naught, which is order of 10 to the power minus 31 kilogram. So we can precisely use the relativistic kinetic energy formula for the corresponding momentum. So this kinetic energy is Pc. Basically, if you remember, E equal to E naught square plus P square C square, okay, or m naught square C4 plus P square C square. So this is the total energy, and this is the rest mass energy. This is kinetic energy. So if it's greater than this, so I can write kinetic energy is Pc, and so Pc is uncertainty in momentum is this much. So you can write uncertainty 1.20 kilogram, and using the value of this, I get 3.3 into 10 to the power minus 12 joule. See, if I divide this by 1.6 electron volt, I'll get the value of 20 MeV. Okay, 20 mega electron volt. So what this result means, that if this electron has to be within the nucleus, then its kinetic energy, the lower limit on its kinetic energy has to be 20 MeV, because it's greater than equal to this, and could be greater than 20 MeV. So if it is to be inside a nucleus, the electron must have a lower limit of energy, kinetic energy has to be 20 MeV. But what happens, that experiments shows that the electron emitted by certain unstable nuclei never have more than a small fraction of this energy, from which we conclude that the nuclei cannot contain electron. So the electron an unstable nucleus may emit comes into being at the moment the nucleus decays. So if this electron has to be inside the nucleus, so if it comes out of the nucleus, if this electron comes out of the nucleus, then this electron has energy approximately equal to 20 MeV. But experimentally, what is found, that the electron which comes from an unstable nuclei is never greater than few MeV. Few electron volt only, I'll say. So the electron which is coming out of the nucleus or unstable nucleus is found to be only of few electron volt, 2 electron volt, 3 electron volt, but never have found that the electron which is coming from the nucleus is of the order of 20 MeV. So that reflects that the electron which is coming from the nucleus is not the constituent part of the atom. So the constituent electron of the atom doesn't resides inside the nucleus, but it actually revolves around the nucleus. And the electron which is coming out of the nucleus in certain experiment, it's just because of the fusion or beta decay process. Like in beta decay process, you saw an electron becoming a proton and plus an electron, and then you have an antineutrino. So this electron is coming because a neutron is getting converted into a proton. Not this electron is not that electron which is a part of an atom. So this is one of the application which says that uh, which says that using uncertainty principle, we can show that the electron cannot be part of a nucleus. Okay, so this is the one application of the uncertainty principle. So if you have been asked that, show that the electron cannot be a part of the nucleus using the uncertainty principle. So this example show you that if electron has to be part of the nucleus, then it has to has a minimum amount of kinetic energy of 20 mega electron volt. But experimentally it has never been observed that the electron which is coming from the nucleus is having such a huge amount of energy. It's only a few electron volt of energy electron have when it is coming from a nucleus. In the same way, if you move to the second example 3.8, which gives you a hydrogen atom is of the order of minus 11 meter in radius. So using the uncertainty principle, estimate the minimum energy an electron can have in this atom. So now we are talking about the atom. In the previous example, we are talking about the nucleus. Now we are asking about the electron which is inside the atom, not inside the nucleus. So inside the hydrogen atom. So we know the hydrogen atom radius is this much, so naturally the uncertainty in position is going to be 5.3 into 10 to the minus 11 meter. So we can find the uncertainty and momentum. So h cross 2 pi, so you can calculate is 10 to the minus 25 kilogram. Now this 10 to the minus 25 we can comparable to the 10 to the power minus 31 kilogram of the electron rest mass. So because these are approximately same, not much difference, so if you calculate it, we can use the classical behavior of the electron. So for finding the kinetic energy, we had to use the classical expression, not as earlier we use the relativistic expression. So for classical expression, kinetic energy is p square by 2m. So this is basically delta p square by 2m. So this is p square, square of this, and 2 into so we get this much of joule when you divide by 1.6 into 10 to the power 19 joule. So we get 3.4 electron volt. So 3.4 electron volt is energy of an electron if this electron is a part of an atom or hydrogen atom whose radius is 5.3 10 to the minus 11 meter. So the kinetic energy of an atom or an electron in the lowest energy level of hydrogen atom is actually 13.6 electron volt. You know the hydrogen atom, this ground state is minus 13.6 electron volt. Then you go up, then you go up, then you go up, then you go up. Similarly, you do, and energy levels increasing. So this electron, which is a 3.4 electron volt of energy, is really established that this particular electron is a part of the hydrogen atom. If this energy comes out to be more than minus 13.6 electron volt, which is the ground state energy of the hydrogen atom, then naturally this electron will not be a part of this hydrogen atom. So now we know that this electron is a part of the hydrogen atom because it is having energy which is less than the energy of the ground state of the hydrogen atom. So now these two examples give the flavor or application of the uncertainty principle, that the electron cannot be a part of a nucleus, or the other one shows that the electron is basically the part of the atom, cannot be a part of the nucleus. Another form of uncertainty principle relates the uncertainty in energy and time, and this is delta E, delta T is greater than or equal to h by 2. Okay, so how we relate energy and time? So time is related with the frequency. Basically, with this relation you can see time is related with the frequency. So when an atom goes to an excited state, and then it this is some excited state, and when it comes back to the ground state, lower state, then it emits a photon, and this photon corresponds to a certain energy. E is equal to, like if energy is E1, its energy is E2, this energy will be E2 minus E1, or this is basically h nu 2 minus h nu 1 if the energy of this is this. So this is equal to h nu. So the uncertainty in frequency and energy is related with this expression that uncertainty in energy is h, because E is equal to h nu. As E is equal to h nu, the uncertainty in energy and the uncertainty in the frequency. And so delta E, because frequency is related with the time, so delta E delta T is related with the uncertainty relation, that is delta E delta T greater than or equal to h by 2 pi. So let us do an example which is related to this uncertainty relation in energy and frequency. Example 3.9. So it says that if an excited atom gives up its energy by emitting a photon of characteristic frequency, so the average period that elapses between the excitation of an atom and the time it radiates. So if an atom excites to an excited state, and then this is the ground state, and then time from going from this to this and emitting a radiation and coming to this is this much. Okay, so find the inherent uncertainty in the frequency of the photon. So if the photon which is coming out, what will be the uncertainty in the frequency of this photon? So uncertainty in energy is h upon 2 delta T, because we know the uncertainty in energy measuring time is 1 into 10 to the power minus 8 second. So this comes out to be 5.3 into 10 to the power minus 27 joule. So if with this is the uncertainty in the energy, so we can find the uncertainty in the frequency by delta E by h, because E is equal to h nu, and this comes out to be 10 to the power 6 hertz. So you can see a lot of difference. So this is irreducible limit to the accuracy. So that means we cannot reduce this accuracy with which we can determine the frequency of the radiation emitted by an atom. So what happens? So as a result, the radiation from the group of excited atom does not appear with the precise frequency nu. So what does it mean? That the actual frequency which the group of atoms which is getting de-excited from this state to this state, we are not actually measuring the actual frequency of those photons which are coming, which are arising out of the de-excitation from this level to this level. So that in this case this will delta nu by nu, which will be divide this by the frequency hertz. This is 1.6 into minus 8. Okay, so in practice what happens, because so this gives rise to, if I measure the frequency, so we are not going to get a peak of precise frequency. In spite of that, what we are going to get a broadened peak. That means the uncertainty in the frequency range, not a particular frequency when the de-excitation takes place. This is this broadening of the peak, or it says as a Doppler effect in frequency, which is due to the uncertainty in energy and time. So I think with this I'll stop here, and the next lecture we'll discuss the next topic. Thank you.